Hi everyone. Today let's talk about chapter 7, inference concerning a mean. Have you ever thought about what if we don't know the mean of the population? How can we estimate it? With the natural gases, well, we can find a sample and then we can measure the sample mean. So hopefully the sample mean is gonna close to the population mean, right? And yeah, that is from our chapter 6. We learned about the law of large numbers. We know that when the size of the sample increases, then the probability of the sample mean close to the population mean is very big, okay, closer to 1. So this natural guess is we can use the sample mean to estimate the population mean. Okay, in general, given an unknown parameter, we want to estimate it by some number that we are able to calculate from the sample data. Okay, so today we're going to talk about the point estimation of a mean. So what is the parameter? Well, that's the population mean mu we want to find. Data, we have a random sample, x1, x sub n. We use capital letters because they are random variables. We haven't observed the values yet, okay? Then the estimator is the sample mean. The sample mean is 1 over n, and then times the sum of all the xi's. Okay, so we call in chapter 6, we have the mean of the sample mean is the population mean. So the sample mean has the same mean as population mean. So it means when we take many samples and then the expected value of the sample mean, it should be close to the population mean. Okay, so yeah, we expected the sample mean of repeated random sample from a given population will be close to the population mean. So now in general, let theta be the parameter of interest, and let theta hat be its estimator, or it can be called a statistics. We call that a parameter is a characteristic of population, and the statistics is the characteristic of a sample. So we talk about that in the first week of the semester. We say population parameter. Okay, for example, the mean. Population mean mu, and then for sample we have sample statistics. Okay, for example our x bar. Okay, so definition: theta hat is said to be an unbiased estimator if and only if the mean of theta hat equals theta. That means the mean of the sampling distribution of theta hat equals theta. A statistic is unbiased if on the average its values will equal the parameter that is supposed to estimate. For example, because the mean of the sample mean equals the population mean, so the sample mean is an unbiased estimator of the population mean. Okay, so besides finding the estimator, we would also like to know how close the estimate is. So we want to find the error term, okay, the absolute value of x bar minus mu, okay, the difference between the sample mean and the population mean. So we call that central limit theorem from chapter 6. We have the standardized sample mean is approximately to the standard normal distribution. Okay, the standardized sample mean z equals to the sample mean minus the mean of the sample mean, which is the population mean, over the standard deviation of the sample mean, which is the population standard deviation, divided by the square root of n. N is the size of the sample. Okay, so this standardized sample mean is approximated by the standard normal distribution. Okay, so our goal. Okay, we know that mu, okay, mu, that's our population mean. We want to use our sample mean to approximate it. But we also want to know how large is the error. If the error is large, oh, that's not good, right? If the error is small, then good. We were more confident about our approximation is good, right? So step 1, questions. Find a range centered at 0. such that the probability z, which is the standard normal distribution, okay, lies in that range equals to 0.95, i.e., we want to find the bound for z such that the probability of z, absolute value of z less than that number equals to 0.95. Okay, let's draw a picture. Do you know what's the picture of the standard normal distribution? Like a mountain, right? And the middle is 0. Okay, so we're looking for a region centered at 0 such that probability of z lies in this region is 0.95. So far so good, everybody? Okay, how do we find that? Well, because the graph is symmetric about the y-axis, okay, about the center mean. So that's why this guy and this guy, the area are the same. And what is the area of them? Well, when we know the total area is 1, so when we add them up, we get 1 minus 0.95, right? Those add up together, then each. So this is 0.05, okay? So each of them has the probability or area 0.05 divided by 2, which is 0.025. So what is this number? What's this the alpha value, okay? Do you remember last time? What's the alpha value? That's when this guy is alpha. So now we know this guy is 0.025. So this number is z 0.025. Okay, and on the left, this is going to be minus z alpha. So that's why from the picture, we know the probability negative z 0.025 less than z 0.025 equals to 0.95. Okay, so when z lies in the region, the interval between minus z 0.025 and z 0.025, the probability of that equals to 0.95. So far, so good, everybody. So from the picture, we can figure out that. All right, next questions. Find the maximum error bound of the sample mean minus population mean with the probability of 0.95. Okay, we just talked about z. What was z? Z is x bar minus mu over sigma over square root of m, right? And now ours, so we have the same picture. So this is our z, right? And this is 0.95, then this is z 0.25. This is minus z 0.25. Okay. But what is z? Well, z is x bar minus mu, okay? So this is the same as, okay, so last time we talked about was z less than this value 0.025. This is 0.95. But what is z? Well, z is x bar minus mu over sigma over square root of n, right? Absolute value less than z 0.025. So far, so good, everybody? Okay. Furthermore, because the standard deviation over the square root of n, this guy is positive, so we can multiply it by both sides. Okay, so we get z 0.025 and we have standard deviation over the square root of n. Okay, so that's why this guy is still 0.95. Now we have to find the bound. So let me use a different color. So this guy is the maximum error bound. Okay, with the probability is 0.95. So far, so good, everybody? Okay. In general, how do we find a maximum error bound of x bar minus mu with the probability 1 minus alpha? Okay, now we have 1 minus alpha, we don't have 0.95, so let's work with that. Okay, so let's draw the picture. So this is a picture. The probability here is 1 minus alpha. Then what's the probability of each piece? Well, those two p's added together is